So in this video, we want to graphically determine the limit of a function that has a removable discontinuity in it. So for this example, we have the rational function f of x equals x squared minus 4 divided by x minus 2. And what we want to notice right away with this function is that we cannot plug in 2 because 2 minus 2 would give us 0 or division by 0 in the denominator. So x cannot be 2 because f of 2 would be undefined. So that's the first thing to notice. The second thing that you want to do when you're graphically determining the limit of a function is to graph the function. So right here is the graph of the function, and you can see that it looks linear, but there's a hole in the function because we're not allowed to plug in 2. There's a hole or open circle when x is equal to 2. But it does look like the ordered pair 2, 4 wants to be a point on the graph of the function. And this tells us right away that 4 is probably the limit as x goes to 2 of f of x. But we want to take a little bit more careful approach to it. So the first thing, we want to understand why the function looks linear, and it does so because the numerator of this function factors as x minus 2 times x plus 2, and it's all over the x minus 2 in the denominator, and x minus 2 divided by x minus 2 equals 1 as long as x is not equal to 2. So as long as x isn't 2, the function simplifies to the linear function x plus 2. So what we want to do when we graphically find the limit is first graph the function. We want to look at the value for which we're trying to determine the limit. What is the limit as x goes to 2, as the inputs approach the number 2 of the function? So we want to look at that, and then we want to establish an open interval centered at the number the input number at which we're trying to take the limit. So in this case, it's a 2. And the most natural thing here to do is just to recognize that the domain of this particular function, because the only restriction is that x can't be 2, the domain is the interval, the open interval from negative infinity to 2, parentheses to exclude the 2, union, and then we can go from 2 to infinity. So this gives us two open intervals centered at 2, which is the value for which we're wanting to take the limit. And then what you do, once you've established the open intervals centered at the input value at which you are trying to take the limit, you let the input values approach the 2 from both sides. So in this case, I'm going to approach 2 from within this first open interval. And notice that this open interval has numbers that are to the left of 2 on the real number line. So what we're going to do is say I'm going to take the limit, and then underneath it you say the limit as x goes to 2, and it has to be underneath the lim symbol here. And we're approaching from the left side. We're going to approach 2 within this interval from the left, and the convention is to denote that as negative. So x approaches 2 from the negative side or the left open interval. So this is a one-sided limit. We're looking at the limit of the function in one of two open intervals. It's the left-sided or it's a one-sided or left-sided limit. So we're taking the limit of the function. So what we want to do is let x approach 2 from within that interval, or approach it from the left. And as we approach 2 from the left, we see that we're walking up the graph towards that hole in the graph, but the outputs are moving upwards towards an output of 4, even though they can't get there because the ordered pair 2, 4 isn't on the line. So it looks like the limit as we let x go to 2 from the left side or from the negative side of the function is equal to 4. And the second thing that you do then is let x approach 2 from within the other open interval. So let x go to 2 from the right-hand side. So the convention is to take the limit as x goes to 2 from the right hand or the positive side. So we're taking the right-handed one-handed limit, so of f of x equals, and now you let x approach 2 from the other side, which means you're coming down the graph towards that hole in the graph, And it looks like as we move down towards this hole in the graph that the outputs are getting ever closer to 4. They get as close to 4 as we want. So it looks like that right-handed or one-handed limit is equal to 4. And now we look at this and we identify that there are 2 criteria that have to be true for a limit to exist. So the first criteria that has to be true is each of the one-sided limits, so in this case the left-sided and the right-sided limits, each of the one-sided limits have to be equal. And the second criteria has to be that the limits are a real number, and we meet both of those criteria. So in terms of a homework assignment, you would say note and then use the graphical evidence to establish the 2 one-sided limits, and then you would draw a conclusion. Note that this is true, and then you draw a conclusion. You say because the left-sided limit, the limit as x goes to 2 from the negative side of the function is 4, and the right, because the limit as x goes to 2 from the left side of the function f of x is equal to or the same as the other right-sided limit, the limit as x goes to 2 from the positive side. So because the limit is the same coming from both directions, both from the left and the right, because they're equal and because they're equal to a real number 4, we draw the conclusion that the limit as x goes to 2 of the function is equal to 4. So kind of the summary is to say, hey, if you can find a real number L, then the limit as x goes to a of the function is equal to that real number if and only if, also written like this, IFF, only if the 2 one-sided limits, the left-sided limit and the right-sided limits, are equal to each other and they equal a real number L, then we say that the limit as x goes to a of the function equals L. So again, that was the criteria that we looked for here. Are the 2 one-sided limits equal to the same value, and is that value a real number? Then the limit exists.